build two suns for the Earth. One sun isn't enough. It only gives us 12 hours of sunlight. We can't work during the other half of the 24 hours without spending too much electrical energy. I don't like her. She seems weird.
Who, Angela? Why do you say that?
Well, her ideas are so out of this world, and I don't know where she gets them. And her arguments are so irrational.
What do you mean by irrational? Does that mean that she's not thinking rationally?
No, not that. I mean, when she talks and reasons, she's not all like us ordinary students. That's why she's irrational. She just think I'm stupid. I can only like her if she'll only try to be like one of them. Good morning, sir.
Morning. You seem to have a problem. What is it? Did I hear one of you say irrational or radical? Perhaps our math lesson today will help you use the words irrational and radical more appropriately. First, I want to tell a rational story. Would you like to hear it?
Yes.
In the beginning, ancient man had few possessions. He could count them on the fingers of his hands and of his toes. Later, however, he needed to count more things of a kind. So he developed counting numbers and simplified these by introducing groups or batches. The Egyptians grouped sets of 10 ones and 10 tens and 10 hundreds. The Babylonians saw groupings by sixes and 12s or 60s. They had what we now call as counting numbers or natural numbers. 1, 2, 3, 4, all the way to n. The sequence is infinite. It could go on and on without end. What is beautiful about it is that he could add or multiply any two numbers in the set, and the result would still be in the set. It had what is referred to as closure. But he needed to have a starting point, 0. So he added this to the set. 0, 1, 2, 3, 4, all the way to n. And this is the set of whole numbers. He could start from nothing and build on it by adding 1, on and on. Later, however, he found out that there were times when the answer to subtracting any number from another was not in the set. Say, 8 minus 12 would not be in the set of whole numbers. And so man had to invent the set of integers, which would include positive and negative numbers, balancing each other on the right and left side of 0 on a number line. Thus the set -3, -2, -1, 0, +1, +2, +3, +4. Since he could not list all numbers to the right and to the left of 0, he used the 3 dots to indicate that the sequence would go on indefinitely.
But I do not always deal with wholes or whole sets. Sometimes I need to work with parts of sets of the same things and with relations between numbers, ratios.
Thus was born the set of rational numbers. A rational number is one which can be represented as the ratio or relation between two integers p and q, where p and q belong to a set of integers. So we have numbers such as 3/4, 5/12, 11/99, which are parts of wholes, sometimes referred to as common fractions. The upper term is called the numerator, the lower term the denominator. If the two are the same or equal to each other, we have what I referred to in an earlier class as a most beautiful and very powerful number called 1, or unity. It is said to be the source or beginning of all numbers because it is used to build and form all other numbers. Then some fractions became special because they took on very special denominators which are powers of 10, like 10 squared, 10 cubed, 10 to the fourth, and so on. And therefore, the rational number family soon included decimals marked by a decimal point. 0.12, 0.008, 3.1414. They're special and different.
But wait, these are not really very different because they can be brought back to their common fraction form like
Now, one can add, subtract, multiply, and divide any two numbers in the set of rational numbers, and the result will still be within the set of rational numbers. Hence, the set has closure. Then one day, someone asked,
Can I find the number which when multiplied by itself will give 10?
Indeed, it was a problem. 3 times 3 is equal to 9. It's short of 10. 4 times 4 is equal to 16. It's far beyond 10. And so many people tried. One said,
It is like having a square whose area is 10, that is. So a side raised to the second power is equal to 10. But how long is the side?
The side is the root of 10. The meaning of the root of 10 is the side which when squared gives 10. Why don't we call it the square root of 10?
a bright idea, since no two numbers could be found which could express 10 as coming from squaring a number. What is the number if n squared is equal to 10? A contest was held.
The square root of 10 is 3.1. 3.1 multiplied by itself is 9.61.
The square root of 10 is 3.11. 3.11 multiplied by itself is 9.67.
The square root of 10 is 3.14. 3.14 multiplied by itself is 9.8596.
The square root of 10 is 3.15. 3.15 multiplied by itself is 9.9225.
But we're getting closer to 10. 3.16 multiplied by 3.16 is 9.9856.
A little more. You're all wasting your time. Why don't we just represent it as root 10? Let's use the symbol for square root. So it is read as square root of 10.
This number cannot be expressed as a rational number. How do we call it then?
Let's use this number as an irrational number.
It turned out there were so many in that family with that family name. So it was also an infinite set, an endless set. And so we have the set of irrationals. So don't begrudge people who are irrational. They too have a place in this world. They are not really odd ones, nor do they come as nerds. They are also members, like the rational numbers. We find, for example, that thousands of years ago, Pythagoras, that master of the right triangle, had the idea of irrationals when he thought of a right triangle with unequal legs and applied his famous theorem, a squared plus b squared equals c squared. But if the legs of a triangle are equal, the relation becomes a squared plus a squared equals c squared. 2a squared equals c squared. c equals the square root of 2a squared. If a is equal to 1, then c is equal to the square root of 2. So 2 is the original irrational number. You can't get them any smaller if the radicand is to be a whole number. Or so we thought. The square root of 2 is not a rational number because it cannot be expressed as the ratio of two integers. And yet we know it exists and that it has a quantitative value. And so are the square root of 3, the square root of 5, the square root of 7. But the square root of 4 is very rational because positive 2 times positive 2 is equal to 4 and negative 2 times negative 2 is equal to 4. The square root of 4 is either positive 2 or negative 2. Since the square root of 4 can be expressed as the ratio of 2 and 1, then the square root of 4 is a rational number. It does not belong to the family of irrational numbers. In the same way that the world is made up of simple folks and complex folks, of rich people and poor people, of oddballs and squares, we have rational people and irrational ones. Like numbers, together we are all people of the world, and we each play a part in it.
So you see, no matter how you dislike the ways of your friend, no matter how you describe her behavior as irrational, she is still a person who has a rightful place in this world. Okay?
And now it's time for our lesson on irrationals. Irrational numbers are sometimes referred to as radicals. They are written with a radical sign. An irrational number, when written, has these parts. This is called the radical sign. N is the radicand. It is the number under the radical sign.
The index is indicated by a small number on the top left of the radical sign. If there is no number there, it is understood to be 2.
This is read as the square root of n. This is read as the cube root of n. In 2 cube root of n, 2 is a coefficient of the radical. Note these relationships. As you can see, extracting the square root of a number is the opposite or inverse operation of squaring that number. To find the square root of a number n, we think of a number which, when multiplied by itself, gives n. Let's try. What term or quantity, when multiplied by itself, gives 100x squared? Rowena.
10x.
25b squared c squared. Pinky.
5bc.
121m to the 6th. Angela.
11m cubed.
144a squared. Pinky.
12a.
36x squared y to the 4th. Rowena.
6xy squared.
16x to the 8th z to the 10th. Angela.
4x to the 4th z to the 5th.
See how easy? It's just like a game called Can You Think of a Number I'm Thinking of if when I multiply it by itself, I get 100x squared.
All the above are perfect squares. Hence they give exact square roots. But suppose we want the square root of 24 or 125a cubed. Example. Do you notice how these are done? When the radicand is not a perfect square, it is separated into 2 factors, such that one factor is a perfect square and the other is not. We extract the square root of the factor which is a perfect square and leave the other factor under the square root sign.
A radical is in the simplest form when the radicand does not have any exponents higher than the index. Rowena.
Can we add or subtract radicals?
Yes, we can, as long as the radicals are similar. That is, if they have the same index and radicand. For example, now these are similar radicals. So we add their coefficients and copy the common radical. Here's another example. Simplify the following. Square root of 20. Angela?
Square root of 5 times 4, 2 square root of 5.
Square root of 72. Pinky?
Square root of 36 times 2, 6 square root of 2.
Square root of 45. Rowena?
Square root of 9 times 5, 3 square root of 5.
Square root of 80. Angela?
Square root of 5 times 16, 4 square root of 5.
3 of the above items are similar because their radicands are all 5. Hence, they are similar radicands.
If the 4 are added, their sum will be 9 square root of 5 plus 6 square root of 2. This expression can no longer be simplified. It is already in the simplest form.
Look at this demonstration of how to extract the square root of 125. Where is the decimal point of 125? Rowena?
125 is a whole number. Its decimal point, although not shown, is after the number 5, written as 125.0000 to infinity.
Right. Using the decimal point as reference, we divide the number into periods of 2.
But why use periods of 2?
We use periods of 2 because we can get 1-digit square root for every 2 digits in the radican. We then do a more complicated form of division, beginning in the first period, which is 1.
But 1 is only 1 digit.
Let me answer Pinky's question. It really is a 2-digit number because we can place a 0 before 1.
She's right.
The square root of 1 is 1. 1 times 1 equals 1. 1 minus 1 equals 0. Bring down the next period, 25. 1 times 20 equals 20. 25 divided by 20 equals 1. 1 times 20 equals 20. And then we add 1. We get 21. 1 times 21 equals 21. 25 minus 21, we get 4. Bring down the next period, 0, 0. We multiply 11 by 20, equals 220. 400 divided by 220 equals 1. Write 1 in the root. 220 plus 1 equals 221. 400 minus 221 equals 179. Bring down the next period, 0, 0. 111 times 20 equals 2,220. 17,900 divided by 2,220 equals 8. 2,220 plus 8 equals 2,228. 8 times 2,228 equals 17,824. 17,900 minus 17,824 equals 76. We can go on and on, but we can stop with 2 decimal places.
The square root of 125 to the nearest hundredth, or 2 decimal places, is 11.18.
It is a tedious method.
That's why people prefer to use a calculator to compute square roots.
In the calculator, we just enter 125 and then press the square root key, and presto!
We get 11.18.
But what if we don't have a calculator?
Necessarily, we will have to evaluate the square root of 125 by longhand.
Don't worry. I'll show you how to come close to the square root by 2 other methods. The first is by using a table of equivalents for basic radicals. For example,
from a table of squares and square roots, we can get these. Then the square root of 125 is equal to the square root of 25 times 5. The 4 examples show that if you have a table for square roots, you can get the square roots of the 4 small counting numbers, say 2, 3, 5, 6, 7. You can use them in extracting the root of some numbers following these steps. Express the radicand as a product of a perfect square number and one of these numbers. 2. Simplify the radical by extracting the root of the perfect square and multiply that root by the equivalent square root of the non-square number.
now apply these to the following by using the table of square roots for numbers smaller than 10. Square root of 242. Pinky?
Is equal to the square root of 121 times 2. Is equal 11 times the square root of 2. Is equal to 11 times the quantity of 1.414. Is equal to 15.554.
3 the square root of 48. Angela?
is equal to 3 square root of 16 times 3 is equal to the quantity 3 times 4 times square root of 3 is equal to 12 times the quantity 1.732 is equal to 20.784.
2 the square root of 180. Rowena?
It is equal to 2 the square root of 36 times 5 is equal to the quantity 2 times 6. The square root of 5 is equal to 12 times the quantity 2.236 is equal to 26.832.
Try this with us.
Square root of 54 is equal to square root of 9 times 6 is equal to 3 square root of 6. We refer to the table of square roots. Is equal to 3 times 2.449 is equal to 7.347. Square root of 75 is equal to square root of 25 times 3 is equal to 5 square root of 3 is equal to 5 times 1.732 is equal to 8.66.
Here is another way of approximating the square root of a number. It comes from the equation of a parabola, y equals x squared.
The parabola is a curve which is symmetric. From y equals x squared, we get the square root of y equals x by extracting the root of both sides of the equation. This means we can get x, which is the square root of any number y, by interpolating between two squares.
For example, what is the square root of 125? The square root of 125 is between the two squares 121 and 144. So we set it up this way. Hence, the square root of 125 is between 11 and 12.
But how do we get the fractional part? In between that is the proportional part. 125 is 4 units more than 121. 144 is 23 units more than 121. Thus, the square root of 125 is 4 over 23 of the way between the square root of 121 and the square root of 144. As a decimal, 4 over 23 is roughly 0.173. The proportional decimal part, therefore, is 0.17. Hence, the square root of 125 is equal to 11.17.
This is only 0.01 below the actual value we got from actually computing the square root of 125 to the nearest hundred.
Estimating the square root this way is a lot easier.
Looks more fun too.
Let's try another example. The square root of 180.
180 is between the squares 169 and 196. Hence, the root of 180 is between 13 and 14. How much is the proportional part after 13, where p is the proportional part? P is equal to 11 over 27, which is equal to 0.41. Hence, the square root of 180 is equal to 13 plus 0.41, which is equal to 13.41.
Compare this with what we get if we simplify the square root of 180 first and then refer to our table of square roots for numbers lower than 10. Do you see how close it is to the result we got from interpolating? Why don't you do the same for the numbers I gave you earlier?
The square root of 75. 75 is between 64 and 81.
Hence, the root is between 8 and 9. It is 11 over 17th of the way between 8 and 9. 11 over 17th is equal to 0.65. Hence, the square root of 75 is equal to 8 plus 0.65 or 8.65.
Try another example.
Square root of 242. 242 is between 225 and 256.
Hence, the root is between 15 and 16. It is 17 over 31 of the way between 15 and 16. 17 over 31 is equal to 0.55. The square root of 242 is equal to 15 plus 0.55 or 15.55.
Compare this with what you'll get if you use the square root key on the calculator.
Square root of 242 is equal to 15.556349. The result we got is very close.
Let me try the square root of 48.
48 is between 36 and 49. Hence, the root is between 6 and 7. It is 12/13ths of the way between 6 and 7. 12/13ths equals 0.92. Square root of 48 equals 6 plus 0.92 or 6.92. If I use the calculator, I get 6.9282032. Very close.
Try estimating the square root of these numbers.
54 is between 49 and 64. Hence, the root is between 7 and 8. It is 5 over 15 of the way between 7 and 8. 5 over 15 is equal to 0.33. Square root of 54 is equal to 7 plus 0.33 or 7.33. Square root of 686. 686 is between 676 and 729. Hence, the root is between 26 and 27. It is 10 over 53 of the way between 26 and 27. 10 over 53 is equal to 0.19. Square root of 686 is equal to 26 plus 0.19 or 26.19.
Well done!
Thank you, sir.
You're welcome. You still have another lesson to learn, Rowena.
What's that, sir?